Hello, I'm Irvin Miller. I've been looking at how math has been taught over the past decade or so, and I've tried to find better ways of teaching it. I recently produced a YouTube called Zero. Math is so easy. And what I decided to do was to apply some different approach to teaching to go over some of the points that I did in that particular video. So let's begin. A much better way to teach math. This presentation is inspired by a conversation between Stephen Strogatz and Grant Sanderson and a YouTube by Justin Sung. Teaching math is an individual conversation between the student and teacher, where the teacher tries to entertain and nurture the curiosity of the student. The student needs to do the studying and collaboration with other students to acknowledge his existence by giving him encouragement, confirming their mutual success, and eager to ask annoying questions to develop a feeling of mastery and satisfaction. This process will highly develop thinking skills and will transform the student's outlook on life. Math also has a sense of honesty and morality. Justin Sung developed 6 levels of thinking, shown from low to a high level. But the levels are not necessarily done in sequential order. They are remembering, which is a regurgitation process, understanding, the ability to explain what you've learned, application, to apply your knowledge. Those levels, every student has ability to achieve. The next 3 levels take a higher level of skill, but they can be developed also. The next step is to analyze, compare what you've done to some other approach. Then you go to a step where you evaluate which approach is better and why. And finally, there's the creation process, where we make speculations and test them out. Now, these particular objectives are not done necessarily in order. And what we're going to do is apply these with some of the other suggestions I've gotten along the way to see how it would change our teaching of some of the concepts I addressed in Math Zero. Math is so easy. Negative numbers are counting numbers. Students' first reaction: I've never been told this is not true. I challenge you to convince me. Counting is an addition process where you count the number of steps to the number off in a distance. So if I'm at the number 9 and I take 5 steps, I will be at the number 14. I need to learn my addition facts. In the conventional approach, I would teach you to memorize your addition facts. However, with this approach, I'm going to teach you a pattern. When you add 9 to another digit, you count back 1 and place a 1 before the number. For example, 9 plus 5, we could look at it as 9 plus 1 plus the 4, which we've counted back to, which is equal to associate the 9 plus 1. So we do that first. We get 10 plus 4. We just put a 1 in front of the 4. Easy. First, we explained how to do the step. Then we showed you how to apply the knowledge, taking us up through the first 3 levels of thinking. We only need to go one more level. You have a contest with a friend where one of you uses the approach just shown, and the other does it through memorization. This allows you to appreciate the advantage of learning a more sophisticated approach. I find that children like this competitive approach and congratulate one another in reaching a certain speed threshold. To get to the next step in the learning process, you encourage the student to ask a question about what happens when you count backward. This is a subtractive process. So we add a number with a minus sign. To get from 14 to 9, we add minus 5. 14 take away 5 is 9. This is a little dicey because we could have looked at this as 14 plus minus 5. As these anomalies allow us to learn something while having limited understanding. You should let the student know that you will learn a more sophisticated way of understanding this. This is where the honesty and morality come into play. Here, you are teaching the student that she or he should challenge and ask a question which you cannot answer. So now let's be a little bit more graphic at this and put up a number line that goes from -5 to +5. In theory, we don't know about these negative numbers yet, but let's see what happens. We go from 2 to 1, we add -1, or subtract 1 and go backwards. We go from 1 to 0, we add another -1, and we hit 0. Okay, if we had not named the 0, it would have now got its name now that we were able to create it or to identify its existence. And then we go from 0 to -1. So we're in essence defining what a negative number is. It's 0, take away 1. We could have also gone from 0 to -2, but we would have taken away 2. So we have at the same time shown that we have a counting process in here, and we've defined new numbers. We have discovered 0, and we have discovered negative numbers. We have done the last 3 steps in the thinking process. One first grader who had learned negative numbers from his older brother wrote down the number line as follows: -5, -4, -3, -2, -1, -0. 0, 1, 2, 3, 4, 5. He was using the symmetry of pattern recognition. I had to compliment him on his cleverness and told him he was not quite right, but later on I would tell him that 0 and -0 occupied the same place on the number line, in violation of the inference that 0 has no sign. I hope you can appreciate the process through which I have gone because I believe my inference has less inconsistencies. I have showed you by reasoning. If you do not agree with mine, then you have to prove to me otherwise, as I have tried to prove your approach to be questionable. But this lesson is more important in that it teaches the thought process needed to to determine the truth of what someone tells you and how to avoid being scammed. Okay, so let's now take this knowledge we have and go a little bit further and see some strange things that happen. Multiplication is a counting process. We have now shown that the negative numbers are accounting numbers, as I so believe. We can eventually define multiplication by the example 2 times 3 is 2 3's added together to give me 6, and 3 times 2 is 3 2's added together, which give me 6. This is an application of the commutative property. What is -3 times 2? We start with the 5th level evaluation by stating that -3 times 2 is equal to 0 plus 2 plus 2 plus 2 equals 6. Well, we know that 2 times -3 is equal to 0 plus -3 plus -3, which is -6. We had assumed the multiplication obeyed the commutative rule that we did not understand but knew it was true. Let's try a different definition. Instead of it being 2 plus 2 plus 2, let's just put a minus sign in front of it. And now we get -6. And now that agrees with 2 times -3 is -6. We may not understand what we have done, but it works. Let's test it. -3 times -2 is equal to 0 plus -2 plus -2 plus -2 is -6. But we have a minus sign in front of it. And a -6 is equal to 6. Little side note. Negative numbers are defined as adding the negative number to its positive inverse and getting the identity element for addition. So if we use the subtraction process and move the -6 over to the other side, we get 6 is equal to 0 minus -6. And this could also be written as -6. So we've now shown that if we subtract a negative number, we get a positive. And now we're consistent. Some little subtleties in there which you have to think about in terms of how this was done. This was difficult for me to understand, but going through these 6 levels of thinking, I could comfortably disagree with what I was taught. So you can see that the thought and psychological process that I use to be confident that my viewpoint is better than what I was taught. Okay, now I really feel confident. And let's go on to another challenge. I know the commutative property works in basic multiplication, but it does not work for matrix multiplication by observation. This is a level 5 thought process. However, the distributive property works for both types of multiplication. Could I derive the commutative property from the distributive property? Let's try. The distributive property says if I multiply a sum by a number, that the result is the sum of the products of that number times each number in the sum. So 5 times 4 plus 3 is 5 plus 4, 5 times 4 plus 5 times 3, and then add them up. Well, 5 times 7 is 35. 5 times 4 is 20, plus 5 times 3 is 15, and 20 plus 15 give me 35. Now, let's try an example. 5 times 1 would be 5 ones. Well, 5 ones is divided by 5. Now, 5 times 3, replace that by 3 ones. And then using the distributive property, I get 5 times 1 plus 5 times 1 plus 5 times 1. I know 5 times 1 is 5. I have 3 5s, so that's 3 times 5. So we went from 5 times 3 to 3 times 5. We just derived the commutative property from the distributive property. For multiplication, the commutative property is not a fundamental property. That is how we were able to come to terms with matrix multiplication not being commutative. I was delighted when I did this because I believed that I had found flaws in the interpretation of other people's work. If you want to share the same pride, you can match my accomplishment. But I may have been missing something. The person, Andrew Wilkes, who solved Fermat's last theorem, had a flaw, which Richard Taylor helped him correct. Collaboration. I hope I am so fortunate that there are others who have done similar work so that I can be talking about collective profit. So let's summarize what we did. The messages in the presentation are somewhat subtle. We know from Gödel's work that the foundation of math are not as ironclad as we would like them to be. There are a number of mathematical statements that are inference, not fact. We address counting numbers, the sign of 0, and the commutative properties as examples. My inference was in direct conflict with the established set of principles that are accepted by the mathematical community. My only solace is that when I apply my inferences, I can solve problems faster and more accurately. This has even worked for my students. A number of well-established mathematicians have been critical of the way we teach math. By combining these concerns with the concept of thinking and the psychology for learning, I have tested that which could be a much better approach than what we have already attempted. I have the gnawing thought, however, that I might be wrong. For example, when I use the rules of operation for negative numbers, then I explain how I had developed these rules. My confidence is based upon my refuting what I observed and being able to prove my concepts to my satisfaction. But what gives you confidence level?